We have Aztec with How to Share a Secret, accelerating private state models with MPC. He will be here shortly in the next few minutes. All right, quick bathroom break, quick stretch break. Let's get the arms active. Yes. Forward, backwards, don't touch the top one. Thank you so much.
Hello. Hey everyone. Thanks for coming to this talk. My name is Zach. I am the CEO of Aztec. We are a layer 2 for Ethereum, where we are ZK rollup with private state. Privacy is a first-class primitive. The idea is that you can have strong encrypted state on chain and still be able to trustlessly transact on that state. So, I'm here to talk about basically the difficulty with encrypted state models on a public blockchain. Basically, before we begin, sorry, it's an old slide. I'll move through this. So basically, Aztec is a layer 2 for Ethereum, as I said, and we are deploying to mainnet imminently. Our testnet is planned at the end of the year. And so creating this kind of network from the ground up is extraordinarily complicated because, I think everyone here has likely probably heard of ZK snark, ZK cryptography, this idea that you can prove statements without revealing underlying data, but actually turning that into a blockchain where I can send value to somebody else without anybody knowing what's going on, or I can call a smart contract and execute program logic that can change some state, and nobody can see what's going on. Including what state is being changed and how. That requires some very ground-up architecture decisions. You can't really retrofit that onto an existing public blockchain. And so I'm going to talk a little bit about some of the struggles that we've had, challenges, open problems for the future, particularly around this concept of shared state. Why is it hard to create encrypted state in a network like Ethereum? How does it even work? And how can we then have this concept of shared state? Let's say I want to create a decentralized exchange, and I want the price that people are getting to be completely hidden. For example, Holy Grail. So why is encrypted state hard? So this is the Aztec architecture diagram at the moment. So this is actually this is like 6 months out of date, so it's bigger now. So I'm going to try and break this down a little bit. So just before I dive into this, how many people here are familiar with UTXOs and nullifiers and Merkle trees? Fantastic. So pretty literate, educated crowd, but given there's about 50-50, I'm going to go through this stuff. The way that a network like Ethereum works is there's a count-based model. The idea is that you have a database that's represented by a Merkle tree. So basically just you take every element in the database, you hash them all together. And if a smart contract changes somebody's account balance, so let's say your Ethereum balance, there's going to be a specific value in that database that's going to change. The problem is that if you, the naive version of working with encrypted state is, okay, you say, okay, I'm just going to encrypt that and use ZK snarks to change its value. Well, the problem there is that you don't actually get strong privacy guarantees, because if 10 different people send ETH to my account in 10 different transactions, there's going to be one specific value in that database that's going to change for every transaction. So you may not see you may not see how much money I'm receiving, but you will see that there is an Ethereum account that is being transacted with 10 times. And in that kind of model, really, your address on that kind of network, it just becomes your encrypted, like the location in the state tree that your balance is stored. So you don't get privacy. The UTXO-based model is more promising, but harder to work with. So UTXO stands for unspent transaction object. So these were originally created for the Bitcoin ecosystem. I imagine their lineage goes back further than that. But the idea is that you have distinct representations of value. So the idea is, instead of having a user with an account that has a balance, each entry in a database represents some quanta of value. So it could represent like Zach owning 0.1 Bitcoin, it could be Zach owning 0.5 Bitcoin. And my balance in that system is going to be the sum of all of the notes that I control. This is more complicated to work with, but it is much more efficient for creating privacy-preserving systems, because now, I'm just going to skip forward. Yeah, okay, and go back. Great. Just want to make sure I'm not missing something. So how do I turn this into a privacy-preserving system where nobody can see what's going on? So one thing that's very easy to do is I can encrypt the UTXO tree database. And say now, if I want to send some tokens in this scenario, I would take an existing node that I control. I would use a zero-knowledge proof to prove that I own it, and that I would basically I want to destroy that node and recreate two new nodes in its place. One where the sum of those nodes' values add up to the total. The idea is one of those nodes is going to be owned by the person I'm sending with. The other one is going to be some kind of remainder left over node I control. Why can this enable privacy? The idea is that this database in a privacy-preserving system, it's append only. You can't delete entries from it. You can't change entries from it. What you do instead is you can just add notes to it. And the way you record a note as being deleted is you have an equivalent database we call a nullifier set, where a nullifier is basically a note, but encrypted under a different algorithm that represents the note being deleted. So the idea is that if I want to destroy a note, I need to prove A, it exists in the note tree, and B, its corresponding nullifier does not exist in the nullifier tree. And then I can destroy it, and I can create two new notes in its place. And in that kind of model, all that an observer sees is that one nullifier has been created and two notes have been created. But they don't know who owns them, they don't know what their values, and they can't link them to any previous transactions. And so you get some extremely strong privacy guarantees. And what Aztec is doing is we extend this concept to not just working with cryptocurrency values. These notes basically contain some arbitrary state, 32 bytes of whatever. And the idea is that there are smart contracts that are deployed to the network that define how to create and destroy these nodes. And so the logic of the smart contract describes what they contain. So that's a bit of a primer on encrypted state. Wait a minute, I've skipped some slides, haven't I? Yes, so I've already explained this. Well, I'll go into a bit more detail. So the idea is, data is an encrypted UTXO node. You take the storage, so each smart contract, like in Ethereum, if you have an Ethereum contract with lots and lots of different variables that change, then they all are given like slot numbers that are unique. And the idea is you take the data, you take the slot number, you hash it with a contract address and a secret, which is missing here, and ta-da, you have an encryption of your state. And then you, a set of notes can represent private token balances. There's basically three ways of doing it. You can have a constant value in your smart contract that can never be modified. That way, it's just a note; it can't ever get nullified. Then you have this concept of a mutable singleton. So you have a value that only exists as one note in the system. It could be like a counter, for example. And every transaction that modifies that value will nullify a note and recreate it. And then you have kind of this hybrid, combinatorial combined system where basically one kind of like synthetic state variable is represented by many nodes. This is how Bitcoin works, for example. And then, this is nullifiers, basically, how these transactions work. But I kind of went over that. And nullifiers break transaction links. So the idea here is that, what the hell is? So basically, you have these nullifier roots, these Merkle tree roots, and the idea is that here this is modeling a transaction where this person's trying to spend a note that's already been nullified, so they can't prove non-existence. So in a layer 2 like Aztec, how does this all get stitched together into some kind of smart contract ecosystem? I've talked about this sort of weird UTXO state model. I've talked about the fact that we prove transitions using ZK snarks, but how do I turn this into like a system where I want to write a smart contract, I want to deploy to a network, I want to send transactions? So the idea is that we represent each function within a smart contract as a circuit. So our programming language for Aztec is Noir. So it can take, it's a Rust-like language that takes, you can write a program in, it gets compiled to a circuit. And a Noir contract can contain multiple functions. Each function compiles to a circuit. And so the set of all, your contract is represented by basically the set of all the function verification keys. You can use these verification keys to basically construct a unique identifier for the circuit. The hash of them all will be a representation of the circuit that is precise. So no other circuit will be able to hash to that same value. So what are some of the problems with the state model? Also, I duplicated state. Sorry, the problems with the state. The high-level goal for Aztec was always to create a smart contract environment with semantics like Ethereum, but with privacy. And so you run into some kind of problems. If you want that very, very high, kind of gold standard for writing smart contracts with privacy, you run into some problems. So I say here local encrypted state because in this kind of model that I've talked about, UTXOs, nullifiers, all private state, all encrypted state is effectively owned by either an individual or a small group of people, because that note has a secret that's required to decrypt it. And if you do not possess that secret, you cannot spend it. And so you can split that secret up into multiple shares and distribute them, or you could have a smart contract which creates multiple notes, basically clones of a note for multiple accounts, so that multiple people can access it. But this kind of abstraction doesn't allow for state that can be shared by an enormous number of people. So to give a bit more context about the abstraction there for a smart contract, so let's take, this is our snippet from our token contract, where we have a private function that performs a, wait, no, that's a public function. Swap public. I think I just, okay, ignore the code, it's too small to read. Imagine this is a private function. So the idea is that when you construct a proof of correctness of this function, what you're doing is you're making a statement which contains a few things. You're saying, A, I am executing a smart contract function. I'm not going to say which one it is, though. And then that function, that smart contract can emit certain actions that have to be followed. So you can either call additional private functions, functions calling functions. You can call what we call a public function. So public functions are basically smart contract functions that don't modify this UTXO state structure. They modify a regular count-based state structure, like on Ethereum. If you need some kind of shared state and you don't mind being transparent, you can do it through a public function. If you want to reveal some information deliberately, you can do it via a public function. You can emit events like Ethereum, but they're encrypted. You can create notes that are encrypted, and you can basically destroy existing notes by creating nullifiers. The idea is like these are the only external actions that are visible when you execute a contract function. And let me just see if I have not quite. Okay, so how we then turn this is just one function though. It's not a transaction. Because you may have a contract that calls contracts that call contracts. What we do is we use this concept of ZK snark recursion to assemble the transaction. The idea here is that if I have a proof of correctness that spits out all of these objects, in Aztec we have this construction called a kernel circuit, which will basically verify this proof and basically process these actions. What do I mean by that? Well, this kernel circuit has a call stack of private functions. The idea is, at the start of your transaction, the call stack has one entry in it, which is the function you want to call. But then, when you create a kernel circuit proof, well, now the output of that may be a call stack with more than one private function, if your contract call calls multiple contracts. And the idea is you continuously recursively run this kernel circuit proof, which it consumes the previous kernel circuit proofs until basically the private function call stack is empty. And so the idea there is that the only things that are visible are basically saying I've executed a bunch of functions, Here's a list of public functions I want to call. Here's a list of encrypted events I want to emit. Here's a list of encrypted notes I want to create. Here's a list of encrypted notes I want to destroy. And that functionally, you can craft things so that all of that information, if there are no public functions, reveals no information. You don't know who you're interacting with. Like, observers don't know who you're interacting with. You do. Observers don't know the contracts you're calling. They don't know like how many of them there are. They don't know what state you're updating. So this abstraction can be used to create some like extraordinarily strong privacy guarantees within a smart contract ecosystem. And so, yes, what was I trying to say here? Sorry, it's been a long week. Yes, this is kind of like more of like an explicit example of what the network sees from this kind of abstraction. So the idea is here I have 3 independent functions I want to call: an account contract to validate who I am, some smart contracts which encapsulates the logic of what I want to do, and then a fee payment contract to pay my fee. And the idea is what's spat out of that is this thing: a proof of correctness, a bunch of encrypted like events and objects to create, and some public function calls. But this, if you don't have any public function calls, this leaks extremely minimal amounts of information. If every transaction creates the same number of notes and nullifies, it leaks 0 information. So the idea here is in this kind of abstraction, you start with proofs on your user device that execute the private LT functions. They get basically rolled up by a L2 rollup service. The idea is because we're layer 2, we roll up, we have sequences, the sequences take transactions, they get proven in a proven network, and in that server-side rollup, that's when the public functions get executed. This has to happen to avoid race conditions, because if you have 2 transactions in a block that modify the same public variable, well, you need to do that in some kind of order, and the sequencer decides what that order is. And then it all gets shoved onto L1 and mined. So, contract tree. We got rid of this. This is an old slide. We don't have a contract tree anymore. Basically, because a verification key is represented by a smart contract is uniquely represented by its verification key, you can just you don't need to store that anywhere in the network to execute a contract. I can answer that in a Q&A in more detail if people are curious. And yeah, the idea is like this is kind of trying to articulate a private state change. Like all of this stuff has to happen on a user's device. The idea is I have to prove that some note exists in a state tree. I need to perform some logic to modify the value. I need to construct nullifiers. And all this needs to be proven client-side on a phone. So that means that we have some rather fierce requirements and targets for our proving system, which is one of the reasons why this kind of stuff isn't widely seen in the wild yet. Problem is, how do you modify somebody else's private state? Here's another kind of issue with these encrypted state models. Let's say I have and why the UTXO system is so important. If I want to send some value to Alice, I don't know her account details. It's encrypted, right? But what I can do is I can create a UTXO note that says this is owned by Alice in a way that's encrypted, but also a way that Alice can decrypt using secret sharing. So again, this is also another reason why the UTXO model is so necessary for encrypted state. Now, but shared private state, that's the kind of the holy grail. There are many like in-progress approaches to this because it's a very valuable thing to do. I think like one of the FHE is a very clear example of how this could be done. However, yeah, there's some performance trade-offs. With FHE, there's trade-offs with everything to do with this. The idea is that why would you want shared private state? Because it eliminates information asymmetries, right? How do I extract MEV if I don't know the values of all the transactions? But it's very difficult to create full information privacy because let's say even if imagine I've created a DEX where in theory the price that people are getting is hidden, right? So if I send a transaction on the network, you can't tell how much value is in that transaction or the exchange price. Well, you can still get that information off chain in some way, right? Because if I'm a user and I perform a trade, I'm going to know what price I'm getting, and so then it becomes a very difficult kind of networking problem, protocol problem to ensure that you can't effectively like DOS the network with queries to kind of get an understanding of what the market is saying. So again, this is kind of an open problem to how to actually generate a truly private exchange with no MEV. You can do it through like commit reveal schemes. The idea is I commit to performing a trade without knowing the price, and then at some later point the trade gets executed and I get revealed the price, but then that has critical user experience problems. How long do I have, by the way? 1 minute. Okay, right. Got to speed through this then. If encrypted state is encrypted, if state is encrypted, shared state, who holds the key? This is kind of the big problem. Because if it's even in an FHE system, right, it's encrypted. Someone has to decrypt it eventually. Who is that person? Some options are you can store the secrets in a trusted execution environment. I would say that's really bad. TEs are very useful, but they have critical weaknesses. They're not secure. It's not a question of if a TE will be broken, it's a question of when. So it's fine to use TEs for short periods of time, for example, to execute MPC protocols, to construct proofs. You don't want to be storing secrets in a trusted execution environment long term. Like, that's asking for trouble. You can split your witnesses into secret shares and evaluate the state transition functions via MPC. This is the best, in my opinion, approach, but this has problems as well, because one of the big issues with MPCs is that you can't tell if collusion has happened. Because what is the consequence of collusion? It's not money gets stolen, it's information gets leaked. If I'm coordinating a DEX, okay, I'm going to try and wrap up. If I'm coordinating a decentralized exchange, right, and I'm using an MPC protocol to keep all the prices hidden, well, if they collude, that means that they can now construct trades that are very advantageous for them and extract value that way, but that's very subtle and it's not obvious, like a 51% attack on Ethereum. And so how do you actually keep people honest? It's really, really hard. And then you can have blinded witnesses when you're using a snark, but that has very similar problems to the MPC issue. Right, I think I've kind of run out of problems, but run out of time. I've not run out of problems, I have many problems. But basically, who decides how secrets are shared? If you have some kind of MPC system, there's lots of open problems about how to coordinate that. Do you have some global MPC set at the protocol level? Do you do it at the application layer? Many open problems. I'd love to chat about them, but I'm afraid I've run out of time. Thank you very much.